In the last video, we left off with a program that I asked you to check out, see if you can figure out what might be wrong with it. Before we do that, let's just maybe review some of the topics that we saw earlier with debugging. Okay, so I've got a bunch of programs here, and if I cat the first one, it's a nice simple program. Remember to compile it, you say Gcc, and you can do it all in one step. By saying gcc -o, whatever output you want to name it to, 1.c. So rather than compiling it into object code and then into an executable file, we can compile it all into an executable file in one step. And as we saw before, this is not enough to really debug the program, but this allows us to run the program. So when we run this, we want to say in the current directory like 16-1, and it works. Then we can try to debug it, but it won't quite do everything we want. Okay, you can run it, and it runs, and it exits normally, so it works. But if you try to set a breakpoint, or if you try to list the program, it'll say no symbol table load, or you might get a slightly different error message on a Linux system. I'm using a Mac OS X. Okay. So what do we need to do? We need to GCC it, but the one thing we were missing was the -G flag for debug. So we use debug mode, and now if you try to GDB it, it'll work. Okay, so this time around, if you say list, if you spell it right, you will get a listing, or the first 10 lines, I believe, and this is much shorter. And we can say break at line 3. There we go. You can run it, and it stops at the breakpoint. We can say continue, and it all runs. Okay, so there's not many variables, not much to look at in that program. So we'll quit out of there. And now we'll say same thing as before, GCC, but this time around I'll do it for the second file. And let me cat it out. Yep. Okay, so here's our file. And it uses printf, so we need the pound include standard io.h. I use the pound define to define a variable. Actually, it's not a variable, it's just remember, it's just a directive to the C preprocessor saying that replace all occurrences of start with 1. So in effect, what it does is it puts a 1 over here. It says n equals 1. Okay. So let's try to debug this. We'll say gdb. Okay. And I can list it. And now if I say list or L, it'll list out 10 more lines. In this case, there's only one more line, so that's all we get. So this is the entire program. So let's put a breakpoint. Let's break at 7, because that's where we have to figure out how this thing works. So at this point, let's just take a quick look at our program. So we pound include stdio.h. That's so that we can use printf. We define something called start, set it equal to 1. So that's basically just setting n equal to 1. And so if you step through this, we have these variables np and q, And the thing to remember about C is that unlike Java, these variables, if all you do is declare them, they are not initialized. In Java, we are so used to seeing variables that as soon as we declare them, are initialized to 0. That does not happen in C, but in this particular program, we do actually set each of these variables to some value before we try to use it. So we should be okay. So that's the kind of thing you want to check for in C programs. Are variables being initialized in the right way? Are they being initialized before they are read? That's the important thing. So in this case, actually everything is fine. So it should say n equals 1, and let's see, we are at 7. Oops, yeah, 7. We are at 7, so we're just about to execute 7. So if you say print n, all right. Oh, we haven't started yet. So let's start it. We'll run. So we set the breakpoint, but we haven't started. So let's run it, and now we are right at 7, and we can do a print n, and it's 1. So you can sort of disregard this. This $1 is actually just referring to n. Okay, and so if you try to print p, you might see some very strange numbers. You might say, well, how did that happen? That's because if you do see some strange values, something other than 0, that's not unusual. That's how C works. So when I say print p, I get this very big number. You might say, how did that happen? That's just because it's reading the contents of whatever memory location is used to store p. And since it was not initialized, it's whatever program was running and using that same memory location before we ran our program. So it could be anything. You run it twice, it might be completely different things each time. Same thing with Q. In the case of Q, we somehow lucked out, and even though we don't need it, we don't need to initialize Q, somehow it was initialized to 0. So we might luck out like that sometimes, but that's not predictable. So you don't want to rely on any variable being initialized at all. You want to do it explicitly. Okay, so let's see where we are. You just say L. We are at line 7. We're just about to execute this. So now the question is, n is 1. So will this put, well, let me back up. N is 1, and n++ we know will increment n from 1 to 2. And the question is, will this put 10 into p, or will it put just 5 into p? The answer is it's 5, because n++ does increment n, but the value of this whole expression, n++, is what's important for p. So even though n is incremented from 1 to 2, the value of n++, that sub-expression, will have the value of the old value of n, which is 1. Okay, so let's check that out. So if that is correct, then 1 times 5 should give us 5 into p. So we will do a step. We could have done a next in this case. Either one is the same. Okay, so now we step, and we are at line 8. We haven't executed line 8. We're just about to. Now let's print n. Sure enough, it's 2. Print p, and if we are right in our thinking that the value of n++ is just 1, even though n is now 2, then we should see a p value of 5. Sure enough, there it is. And so let's print. And I think we can use the abbreviations from now. Say instead of p, you can say, instead of print, you can say p. So p, q. That looks kind of cryptic, but what that's really saying is print q. It does look doesn't look that readable, does it? But you can do that once you're used to the commands. You can use abbreviations. All right, so now let's do a next, and you can abbreviate that to n. Okay, so there is next, and we'll print Q, what should Q be? So let's take a moment and think about it, and you can pause this video if you want and think about it. Remember that we incremented n from 1 to 2, so we saw that here. Now what we're doing is we're saying increment it again, basically. So n, once we've stepped over that statement number 8, where we were, and now we're going to execute number 9, the printf. At that point, n is definitely incremented. So n is definitely 3. So let's try that out. N is definitely 3. Okay, so then the critical thing as far as figuring out what goes into Q is what is the value of plus plus n. It turns out the value of plus plus n is the new value of n, which is 3. And so this will be 3 times 5 is 15, so Q gets 15. And so you might think about that for a little bit, but let's check it out. Print Q is 15. So make sure that makes sense to you. Why P got the value 5 and Q got the value 15. When you look at it for the first time and you're not used to the plus plus, n plus plus, or plus plus n, the differences between them, you might think that there's something wrong. No, this is how it's supposed to work. P should have the value 5 and Q should have the value 15. Everything is working as it should. Okay, so now if you do a next, and you don't want to do a step. If you do a step now, you're telling GDB that you want to step into the printf function, which you don't want to do, and I don't think you can do it. So what you want to do is next. So say next or n, and then what you see is all of this stuff printed out. N is 3, P is 5, Q is 15, and we're at the next line, the return statement. So we can say continue at this point. And I think C might be enough. Yep, C is enough, and we continue, and the program exited normally, and we can quit. And you can run this program any number of times if you're in GDB.